Okay, so welcome back. We are in chapter 6 now. So chapter 6 deals with pollutant control method. Previous chapter, we discussed the mechanism involved in forming pollutants. So here our focus is only on primary pollutants. We have four primary pollutants emitted from IC engine. Here we are discussing in this chapter, we are discussing about the control methods that are available to reduce the pollutant. So this is very important to know, because as we know that there are legal mandates. So we need to reduce the concentration of these four primary pollutants below some legal limits. And these legal limits, I will briefly discuss in the last chapter. It's going to be different in different countries. In India, we have our own legal limit. Currently, we follow BS6, Bharat Stage 6 emission norms. So accordingly, the concentration of these pollutant levels should be reduced. Otherwise, new vehicle cannot be launched in a market until otherwise these legal limits are met. So we need to spend a lot of money and we need to spend a lot of time to reduce the concentration of these four pollutants. Okay, otherwise we cannot, from the OEM perspective, the vehicles cannot even be launched in the market. So this is very important to understand what are all the available methods to control or reduce the pollutant concentration. Broadly, they are of two categories. One is in cylinder, other one is after treatment. In this method, we reduce pollutants inside the cylinder. Here, we are reducing pollutant in the tailpipe before the exhaust gas is discharged into atmosphere. So this chapter basically deals with the available in-cylinder methods and after treatment control method. I have started this discussion in the last class. I will continue that. So in the in-cylinder control method, pollutant control method, in the last class, we discussed about this EGR, exhaust gas recirculation method, combustion chamber optimization method, which is applicable, both the methods are applicable for SI and CI engine. Injection parameter optimization method is adaptable for spark compression ignited engine, CI engine. We are optimizing injection parameters like injection timing, injection pressure. We also go with split injection, as we have discussed in the previous class. So all this are applicable for in-cylinder fuel injection. You know, in an SI engine, we inject fuel outside the cylinder. It's a port injection. So for port injection, these parameters, injection parameters, do not have any significant influence on the pollutant level. So that's why I say that this is more adaptable for CI engine, compression ignition engine. Then we also discuss this variable valve timing system, wherein we can vary the timing of intake exhaust valve open and close using a variable timing system. With that, what you can do is you can vary two things. One, the residual or the products of combustion that remains in the cylinder can be varied. Suppose if you want to control NOx, so you can increase the residual gas concentration. You know, it is like internal EGR. Residual gas is also called internal EGR. It's nothing but products of combustion. Retaining more EGR inside the cylinder is going to influence NOx formation. As we know, the primary effects are there will be drop in temperature, drop in oxygen concentration in the cylinder if you retain more exhaust in the engine cylinder. So by having a variable valve timing system, if you notice that the NOx levels are very high, you can retain more residual in the cylinder. That way you can have a control over NOx. Similarly, unbound hydrocarbon also can be controlled using a system that can vary residual gas. Okay, we have discussed how we can do that in the previous class. In fact, we have designed mechanical as well as we have two patented technology developed by our group. One is a mechanical variable valve timing system, wherein we varied the cam profile, right, to achieve. We varied the profile, right? You know, the valve actuation is based on the cam profile. So we could have a variable cam profile, and thereby we could vary the timing of the valves. So that's a mechanical system which is more durable. We also have developed an electronic patented variable valve timing system. By using this, you can vary the timing of the valve, that you can vary the residual gas fraction and control NOx and HC using such a system. We also have seen that with a variable valve timing system, you can also vary the effective compression ratio. Effective compression in the cylinder starts only after the intake valve close. Until then, the compression won't be effective. That's why we have a terminology, effective compression ratio, that starts from IVC point. Okay, so you can also change this effective compression ratio by changing this intake valve closure timing. It can be here, it can be here. Accordingly, you are varying the effective compression ratio. Based on that, the temperature, in-cylinder temperature will be varied. Suppose if you increase compression ratio, you know temperature is going to be high. If you reduce compression ratio, you are going to have a less temperature. So based on the pollutant control method, you can increase or decrease. For example, if you want to increase the oxidation rate of SC and CO and soot oxidation rate, you have to increase temperature. Suppose if NOx levels are high, you have to reduce the temperature. Okay. Really, what is done is you will have a closed loop control system with sensors that will continuously monitor the pollutant levels in the engine tailpipe. Accordingly, you have to adapt a suitable method. So you have multiple options available as we are looking at here. You have to use suitable method based on the control that you want to have, right, in any of these primary pollutants. Next, we have downsizing and supercharging, which is adaptable for only spark ignited engine. So here we reduce the size in the sense that we reduce the displacement volume. That is what is downsizing. You know, when you reduce the size or capacity, the power rating will come down. We don't want the power to come down. That's why we do supercharging to retain same power as a larger capacity engine. So this combination of downsizing and supercharging is very effective to control SCCO, because the fuel economy will considerably improve if you do the downsizing. Friction losses especially will come down significantly. Lower friction losses will reflect in better fuel economy. So this is a quick recap of what we have discussed in the previous class about in-cylinder control. Now we are going to start with fuel modification based approach, which is again an important in-cylinder pollutant control method, which is adaptable for both SI engine and CI engine.
Sir, I have a question. Can I ask if you allow?
Yes.
Sir, basically, this downsizing of the engine will reduce the friction and flow losses that you have told us. And to retain the power, we have to introduce supercharging, right, sir?
Yes, yes.
Now, supercharging will also consume some power to run in that way. So whether that power will be, what I mean to say is lesser than the friction losses that engine can occur?
No, always there is a trade-off. This is what I said in the beginning. Always, see, if you have to do supercharging, you are using a compressor. Okay, so right, that will consume some power, but that is more effective in the sense that the power increase you get with supercharging. What you get with supercharging, you are increasing rho, right? In the sense you are increasing burning.
Yes.
So you have an increase in P because of burning more mass. This increase in P should be higher than the increase in P due to power consumption by the supercharging. Already, otherwise it's uneconomical to go with supercharging because there is additional cost involved, right? Not only power.
Okay, sir. Got it.
Generally, the power consumed here is negligible compared to the power increase you get.
Right, sir. Thank you.
Fine. Okay, so now here we are looking at fuel modification based approach, which is applicable for both. Can you please mute your mic? So I don't know how you are able to listen. I always have this doubt. If you have a background noise like this, it's very difficult to follow. Is it fine? Everything is fine there?
Yes, sir. Things are okay, sir.
Okay. So next we are going to look at fuel modification based approach, which is applicable for spark ignited engine as well as compression ignited engine. So here, when I talk about fuel modification, we are going to discuss what type of alternative fuel that you can use compared to gasoline or diesel. Gasoline is a conventional fuel for spark ignited engine. Diesel is a conventional fuel for compression ignited engine. Of course, chapter 1 is devoted to understand more about these two conventional fuel, which are being extensively used for more than 100 years now. Okay, so these fuels are extensively used but from the pollutant reduction perspective, you can go with running engine with some alternative fuel. Already you are seeing that on road we have several alternative fuel powered vehicle like LPG, CNG, Okay, you are seeing it. Okay, so here we are going to look at what kind of alternative fuel options are available and how it helps in reducing the pollutants from SI and CI engine. So this slide shows a quick summary of what are all the options, alternative fuel options you have for gasoline. You have alcohol, any alcohol fuel, methanol, ethanol. So you have many alcohol fuels like C1 is methanol, 1 carbon. Here ethanol you have 2 carbon, propanol 3 carbon. Okay, butanol you have 4 carbon. So you have different alcohol fuel starting from methanol with a different carbon chain length. Okay, and all these are suitable to be utilized in gasoline. In fact, in US, if you go to any pumping station, you always have a blend of gasoline and ethanol. 10% ethanol and 90% gasoline is what is a fuel available in US pumping station. So there they have almost made it mandatory to use 10% of ethanol. Ethanol is available there because they have it's a agricultural residue based ethanol. The source for ethanol is agricultural residue based. Okay, for example, corn can be used to produce ethanol. So it's a biofuel compared to gasoline, which is not a biofuel. This is renewable. Okay, so you can use alcohol fuel. You can use natural gas. Natural gas is methane. Okay, CNG is compressed natural gas. So we see in Delhi, in other metropolitan cities also, we have the CNG powered vehicle. And you have to compress this natural gas, which is methane, to a high pressure level of 200 to 300 bar to meet the given vehicle mileage. Because it's a gaseous fuel, power density is poor, volumetric energy content is poor. That's why you have to compress to this level, pressure level. LPG is liquefied petroleum gas. It's extensively used for cooking. The primary purpose, the primary target application for LPG is domestic cooking, but we can also use it in engines. Okay, so here LPG is used because better anti-knock, high octane fuel LPG is. I will talk about the composition next. This compared to natural gas, here you need a lower pressure to store it, only 4 bar to 20 bar. If you compress it, this will liquefy. It will be stored in a liquefied condition. That's why it's called liquefied petroleum gas. Once it is released, once the pressure is released, okay, once it reaches ambient pressure, it will be in the gas phase. Normal ambient condition, it is in the gas phase. Once you compress to this pressure level, it will be in the liquid phase. So it's easy to store once you have in the liquid phase. Okay, it will increase the volumetric energy content. That's the reason. Hydrogen, it's the lightest gas. We already discussed about this. It's not a safe fuel, but still there is an interest to utilize hydrogen. Recently also you would have witnessed the government of India has allotted a lot of money to do research work on hydrogen. Okay, they call it as a green hydrogen mission. Several crores of money has been recently allotted to utilize, encourage large-scale utilization of hydrogen in internal combustion engine. So hydrogen, one of the important reason is having better anti-knock characteristic, better combustion characteristic compared to gasoline. Of course, you have to compress it to a very high pressure compared to CNG. Here you have to compress it to 700 to 800 bar. And the primary interest is there is no carbon in hydrogen. So there are no carbon-based emission. Unborn hydrocarbon, carbon monoxide or carbon dioxide won't be there with the hydrogen combustion because the fuel do not have any carbon. There will be few carbon emission. The source is not fuel, the source is rather lubricating oil. Oil will become a source for producing some carbon emission, but that is negligible. Okay, so this is the alternative fuel option. On what basis we have chosen this as an alternative fuel for gasoline? By looking at this fuel, can you comment on what is the common feature in all this? And what are the fundamental characteristics already discussed in the very first chapter?
You should have aromatic content and olefin. Olefin and aromatic should be in higher content.
No, that is with respect to gasoline composition. What I am asking is with respect to fundamental
high anti-knock property.
Anti-knock property. Good. Anything else? Two important property I said for SI engine. For SI engine, there are two fundamental requirements.
And volatile, sir.
Volatility, sir.
Volatility.
And less reactivity.
Yes. high volatility, low reactivity, or better anti-knock. Low reactivity and better anti-knock are interrelated. You know that. Okay, so this is also a better anti-knock or high octane number. So this two criteria should be satisfied. Otherwise, you cannot use a fuel for SI engine application. You could see that in all this fuel, these characteristics are satisfied. Alcohol is highly volatile compared to gasoline. Its boiling point is much lower. It's a single component. Methanol, if you take, its boiling temperature is around 50, 53, 55, around that number. And gasoline, you have a range 20 to 200, up to 200. So this is volatile. Natural gas, LPG, hydrogen, of course, are gaseous fuel. There is no question of volatility. Already they are in the gas phase. Okay, and all these are low reactivity fuel in the sense that they have a high octane number. High octane number fuel, the advantage is that there is no knock problem. So you can even increase compression ratio if you run SI engine with this fuel. You can increase compression ratio, that you will have a benefit in thermal efficiency, right? When you increase compression ratio. So this is a reason. Now, from the pollutant reduction perspective, let us look at what these fuels are doing. So as I said, we have this characteristic, better anti-knock characteristic and high volatility characteristic. Alcohol fuel, what they will do from a pollutant reduction perspective, they have the potential to reduce SC, CO. How they reduce SC and CO? You know, in SI engine, you have three primary pollutants, SC, CO, and NO. We are looking at how these fuels, alternative fuel, help in reducing this. SC and CO can be reduced because alcohol fuels are oxygenated fuel. They contain very high fuel bound oxygen. Here you should note that compared to oxygen present in air, if the fuel itself has oxygen, it's highly reactive. So this fuels, methanol, if you take, it contains almost 50% oxygen, inbound oxygen. It's also called fuel bound oxygen. Fuel itself has around 50% oxygen. So since this fuels have oxygen inbuilt, fuel bond, okay, they can result in complete combustion. Okay, insufficient oxygen is what is causing partial oxidation. Now, fuel itself has oxygen, so it will help in creating more complete combustion. So you can expect a reduction in SC, reduction in CO. NO will also come down primarily due to latent heat. These fuels are having high latent heat of vaporization. You know, any fuel with a high latent heat of vaporization creates something called cooling effect, because they are going to absorb temperature from the cylinder. Due to absorption of higher heat from the cylinder, they are going to result in drop in temperature. Drop in temperature will help in controlling NO effectively, thermal NO effectively, you know that. So we can say that all the three primary pollutants can be reduced with alcohol fuel, but you could see that there is a trade-off. Oxygen will result in complete combustion. Temperature reduction may also try to increase SC and CO. So you have to use alcohol fuel with a lower blend level. When you use it to a lower extent, you won't have the problem of high SC or high CO. Generally, they are used less than 50% level. Okay. Gaseous fuels, LPG is liquefied petroleum gas. It consists of only two hydrocarbons. One is propane, other one is butane. The proportion of propane and butane is different in different countries. In India, we have 60% butane, 40% propane. This is what we use for domestic cooking. Same thing, you can use it for vehicle propulsion. Okay, propane 40 and butane 60%. You could see that these are very simple hydrocarbon fuel compared to gasoline, which is a complex multi-component mixture. Here you have only two hydrocarbon, and it exists in the gas phase under ambient conditions. So you have a much better fuel air mixing. You have a homogeneous engines emit very high SC and CO at the time of starting or warm-up stage, because you have a problem of vaporizing gasoline. We already discussed about that. Liquid phase fuel vaporization problem always exists. If you use a gas phase fuel, there is no vaporization problem. It is already there in the gas phase, so it will blend well with air, mix and combust well. So you will have more complete combustion that will reflect in less SC, less CO. Same is the case with CNG, compressed natural gas. Primary component is methane. Other gases are minor constituent. Primarily methane above 90%. That's what is CNG. So again, it's a gas phase fuel. You can expect a reduction in SC and CO. So gaseous fuels result in HC and CO. Alcohol fuel in a blend level will help in reducing all the three primary pollutants. Okay. Now let us look at the options we have for diesel. Okay, for CI engine application. For CI engine application, you have these different fuel. What is the criteria we need to have for CI engine application? Fundamental criteria, fuel criteria.
It should be high reactive and
Less volatile.
less volatile.
Volatility doesn't matter. No need to have a low volatile. It can be high volatile also. Volatility is not an important consideration. The primary consideration is high reactivity, meaning cetane number should be high because it's a self-ignition process. Self-ignition or auto-ignition. So what you need fundamentally from a fuel perspective is you need to ensure that that the fuel will self-ignite or auto-ignite. Okay, so it needs to have a minimal cetane number. We have discussed that this should be at least 40 according to Indian specifications, right? Not 40, it's above, according to US specifications, around 40. In India, it's around 50. We already discussed all this in chapter 1. So CN should be much higher than 40. Otherwise, there will be problem of self-ignition or auto-ignition. Okay, so now when you look at the options you have, alcohol, natural gas, and biogas are also listed here, but these are not high cetane fuel. You know that alcohol is a high octane fuel. Just now we discussed about that. Then why we are interested in alcohol? Then what should we do? This is not a high cetane fuel, it's a high octane fuel. So what should we do to utilize alcohol?
It should be mixed with a very lower proportion that way.
Lower blend level. That's what I have indicated here. Methanol, ethanol, or any other alcohol. So here you should note that when you increase the carbon chain of alcohol, the octane number will come down, cetane number will increase. Higher carbon chain alcohol will have better cetane number. That also an important point to be noted. But generally, these fuels will have high octane or low cetane. So you have to use it at lower blend level. Okay, otherwise you will have a problem of self-ignition. But the interest again in using alcohol fuel for CI engine is emission reduction. I will talk about it. Natural gas or biogas, again, these are high octane fuel. They do not have a high cetane number. Then how do we use this fuel in diesel engine? You have to use it in a dual fuel mode. So you cannot use natural gas, biogas alone. You have to use it along with diesel. That's why it is called dual fuel mode. Diesel acts as an igniter. Because diesel is a high cetane fuel, it helps in igniting this fuel. So what is done? Natural gas or biogas will be injected using a port injection system. Pre-mixed natural gas or biogas is ignited using direct injection of diesel. That is how this dual fuel engines operate. Okay, you are using two fuels simultaneously. The primary fuel is natural gas or biogas, and diesel is a pilot fuel which is used to ignite this fuel. Otherwise, this fuel won't ignite. Then you have something called DME. These three fuels are high cetane fuel: DME, biodiesel, and FT diesel. FT is Fischer-Tropsch diesel. Fischer-Tropsch diesel is also called synthetic diesel. It's a person name actually who discovered the process to produce this fuel. DME, biodiesel, and Fischer-Tropsch diesel. DME is dimethyl ether. So these fuels have high cetane number. That's why they are preferred for CI engine application. Unlike the other two, alcohol and gaseous fuel like natural gas or biogas, we can, in fact, we can also list hydrogen here. In a dual fuel mode, you can also use hydrogen in CI engine. So this dimethyl ether, the source is synthesis gas. Synthesis gas is a blend of CO and H2. This is what a synthesis gas. You can generate this gas from non-renewable source like coal. You can also produce the synthesis gas from renewable sources like biomass. It can be any source. Okay, it's preferable to go with renewable source CO and H2. From CO and H2, you will get this dimethyl ether. Similarly, Fischer-Tropsch diesel source is synthesis gas. Okay, so this can be used as an alternative option for diesel. Now let us look at from the emission perspective how they are reducing pollutant emission. So you need to look at better ignition delay, which is a fundamental criteria. for choosing an alternative fuel for CA engine. Alcohol fuel should be used at lower blend level. And what is found with alcohol fuel with lower blend level, they can reduce CO2, SC. For the same reason, whatever we have discussed earlier, they can result in more complete combustion because they contain oxygen. For the same reason, they can reduce particulate emission. It helps in soot oxidation. Soot is a major component in particulate matter. Since the fuel has oxygen, it helps in reducing particulate matter. And as I said, this fuel has the potential to reduce temperature because of high latent heat. Okay, so they can bring NO levels down because they can reduce temperature in the cylinder. So you can see here that alcohol fuel at a lower blend level can bring down all the 4 primary pollutants. Okay, all the 4 primary pollutants in CA engine. So this is where we have an interest in using alcohol fuel. Biodiesel, the source is vegetable oil. It's a renewable source. Any oil, vegetable oil, cooking oil can be used. Even non-edible oils can also be used, including the waste oil from restaurant. So waste, so you know that you should not recook, you should not reheat the oil. Reheating oil multiple times has a potential to cause cancer because the molecular structure of vegetable oil, right, when you start reheating again and again, okay, its molecular structure is going to be different. Okay, so naturally found oil will have something called a cis structure, which is a bent structure. When you reheat oil multiple times, it will lead to trans structure, which is a straight line structure. This can block your heart or any other blood vessel. That is one thing. Okay, so so reheating of vegetable oil is not advisable because the molecular structure is changing. So you have to dispose oil. So you have a large disposed oil that you can convert it into these fuel, okay, by doing chemical treatment. By chemically treating this waste vegetable oil, you can convert them into useful fuel, biodiesel. Advantage in using biodiesel from an emission reduction perspective is you can bring down CO, SC, soot. This is possible because the fuel contains 11% oxygen, inbuilt oxygen. For the same reason, NO will slightly increase because of fuel-bound oxygen and higher temperature that biodiesel create. Okay, so NO level will be slightly increased, and this fuel CT number is higher than diesel. So it is a preferable fuel. Only thing, OEMs like Bosch or Delphi, they don't give any warranty for their injection system if you go with biodiesel. Okay, one of the potential problem with this fuel is it may oxidize over long usage, and because of that, it is not compatible with some of the materials that are used for injection system. So you need to redesign your injector, which the OEMs resist to do it. That's the reason why this fuel is not used in a larger extent, okay, in engine, current engine. Fischer-Tropsch diesel, it's also called synthetic diesel. The source is synthesis gas. Synthesis gas is CO plus H2. So through a chemical treatment, you can convert this synthesis gas into Fischer-Tropsch diesel, which contains primarily normal paraffin. Unlike conventional diesel, which contain different hydrocarbon classes, this fuel contains primarily normal paraffin, okay, up to 90%. CT number of this fuel is around 70, which is much higher than diesel. Also, one of the important feature of this fuel is you can see that it can reduce all the 4 primary pollutants, CO, SC, NO, and soot. CO is reduced because the fuel consumption, Fischer-Tropsch diesel is a high heating value fuel. So it is enough if you consume less fuel to produce a given power output. So CO levels will come down because of better fuel economy. SC will come since this fuel do not have any aromatic, NO will come down. For the same reason, soot will come down. You know, aromatics produce soot precursors through pyrolysis process. Since this fuel do not have any aromatic, it brings down soot level. Okay, so this is a fuel that has a potential to reduce all the 4 primary pollutants from diesel engine. Only problem with this fuel is the cost of this fuel is high. That's why it is not commercially successful. Like CNG or biogas or even hydrogen can be used in dual fuel mode. The advantage with this fuel is you can simultaneously bring down NOx and particulate. It creates a better pre-mixing. You have a gaseous fuel injected as a primary fuel. Diesel is only used as an igniter. Diesel has aromatic that increases NO and soot. If you use this gaseous fuel as a primary fuel, since they don't have any aromatic, you can bring down both NOx and particulate matter. The primary advantage of running engine in a dual fuel mode is you can simultaneously reduce NOx and particulate emissions. Okay, so next we are going to discuss about an important research aspect that is applicable for pollutant control aspect that is applicable for CI engine, which is called combustion mode modification. So this is the area where our research group is currently working on. So I will briefly talk about this combustion mode modification, which is applicable for CI or diesel engine. And with this combustion mode modification, you can bring down NOx and particulate matter to near zero level. So almost zero levels of NOx and particulate you can achieve if you do combustion modification in the CI engine. Now let us look at what we are doing here in terms of combustion mode modification. So you know conventional diesel engine result in very high NOx, very high particulate. This is what is a conventional combustion. Very high NOx because the flame temperatures are very high. Okay, well above 2000 K. That is the threshold limit for forming NO through Zeldovich mechanism. It's also evident here in the right-hand side plot where the NOx formation regions are shown with respect to temperature. Y-axis you have equivalence ratio. X-axis you have temperature. You could see that NO start to form around 2100 K, right? And you have a very high NOx level when the temperatures are high. So high temperature is a primary cause for forming NOx. Conventional diesel combustion, this blue one is a conventional diesel operating regime. So it passes through the NOx formation region. So you end up in forming very high NOx. Soot will form with the equivalence ratio starting at 2, as you could see here. This is a soot formation region. So 2 to 4, as I said, is an ideal soot formation regime, and the very high soot levels will be there when the equivalence ratio is very high. So this is the region, equivalence ratio and temperature region, where you have a very high soot formation. Conventional diesel engine operating condition will pass through very high soot formation region, very high NOx formation region. You cannot avoid soot or NOx formation when you run engine in a conventional combustion. That's why we have an alternative combustion shown in green color. This is called a low temperature combustion mode. Having understood that soot is formed with a threshold feed value of 2 and NOx forms with a threshold temperature value about 2100 or so, the operating regime, you could see here that it is carefully designed in such a way that you are bypassing soot formation, you are also bypassing NOx formation, meaning you are running engine at a lower temperature, you are running engine with a low equivalence ratio. Low equivalence ratio, low temperature, if you are able to run, you can completely eliminate formation of NOx and soot. This is what we are doing in this low temperature. This low temperature is a relative word. Compared to conventional combustion, the operating temperature is less. So this combustion mode is referred to as low temperature diesel combustion mode. Okay, with this you can eliminate NOx and soot, but the problem here is controlling timing and rate of combustion is difficult. You have a narrow engine operating regime. Okay, widening the operating regime is a major problem here. This is what I am looking at currently. We need to redesign engine. We need to redesign fuel because conventional diesel and conventional engine design can adapt only to this conventional combustion. When you talk about alternative combustion, you need to redesign engine. You need to redesign fuel. This is what I am currently working on to make this a commercially successful combustion mode. Okay, thereby you can completely eliminate NOx and soot. So what I will briefly talk about its principle, what we are doing here. So, you know, in a conventional combustion mode, you have start of injection, the combustion will get started before the injection event ends. So before the end of injection, the combustion event will get started with a start ignition delay. Short ignition delay time will be there between start of injection and start of combustion. Okay. So after this start of combustion also, you continue to spray fuel, inject fuel into the engine cylinder. So end of injection is happening after the start of combustion. This is what we refer as negative ignition dwell. What is ignition dwell? Ignition dwell is the time period between end of combustion, end of injection and start of combustion. The time period between end of fuel injection and start of combustion event is referred to as ignition dwell. In a conventional combustion mode, this is negative because you see here that combustion is getting started before the end of injection. Whereas in this alternative combustion mode, what we do here is this is start of injection, this is end of injection. After the end of injection, the combustion will get started. So you have something called a positive ignition dwell. Combustion is going to start only after the injection event is over. This is the primary difference between these two combustion concepts, conventional and low temperature. In a conventional mode, end of injection start after the start of combustion, whereas here the end of injection happens before the start of combustion. So the entire injection event is over. So you have injected all the fuel. So once all the fuel is injected during this period of time, what will happen? Pre-mixing. So you are pre-mixing fuel and air, okay, before the combustion even gets started. That's why you are able to achieve pre-mix lean combustion. In SI engine also you do pre-mixing, okay. Your injection event is over before the start of combustion. You start combustion with spark discharge, but before spark discharge, you know that the injection event, port injection event is over well ahead of spark discharge. There also it is pre-mix, but the difference between this pre-mix and that pre-mix is here you have a pre-mix lean combustion. Phi is around 0.4 here, okay. Whereas in SI engine, phi value is 1.1 above stoichiometry generally, okay. So here it is pre-mix, but it is lean. So with this, what we are trying to achieve is phi global is equal to phi local. Phi global is equal to phi local. Since you have an overall global value of lean, right, 0.4, the local value will also approach that because I am doing pre-mixing. Because of this, you will be able to run engine in this domain. You will be able to run engine in this domain of equivalence ratio and temperature, wherein local equivalence ratio is well below 2. You are not forming soot. Temperature will be less because you have excess air. Pre-mixed excess air, pre-mixed fuel air with excess air, very high excess air level. Okay, equivalence ratio is only 0.4. So temperature will come down below this threshold value. You will be able to eliminate NOx formation. You will be able to eliminate soot formation. Clear?
So, sir, here you are completely eliminating the undermixing phase, right, sir? Undermixing of the fuel.
Yes, yes.
So diffusion phase will not have any fuel injected in the
You
combustion.
don't have a diffusion phase combustion. That is exactly happening here. In a conventional mode, due to negative ignition dwell, you have a diffusion phase combustion. Here you are eliminating diffusion phase combustion. You have only premix.
So, sir, in this combustion mode, will there be there's a dominant premix phase, right, sir? If I'm not wrong.
It's only dominant. Yes, it's only premix phase combustion.
So only SC emission will be a problem for this. Like we have
SC
to.
and CO will be high. Why? Because the temperatures are less, so oxidation rate of SC and CO is very low. Your engine operating temperature is less. Because of this, the oxidation rate of SC and CO will come down. You will have a problem of SCCO. But more severe problem is NOx and PM. You are going to eliminate that. Okay. SC and CO is less severe, I would say, compared to high NOx and high PM.
That can be taken care by catalyst. So
yes, I will talk about that also. That can be taken care by DOC, diesel oxidation catalyst.
Thank you, sir. Thank you. Thank you for this idea.
Sir, one doubt here. Will this have any impact on diesel knocking because we are increasing pre-mixed combustion phase?
It's a very good question. The knock, we always, when I say I'm running engine in this LTC mode, you always run closer to the knock limit because you have a pre-mix combustion, right? it is highly sensitive to phi value. When you start increasing phi, you will have knock. That is why I said you have a narrow engine operating regime. What I mean to say here is when you try to move towards high load, you may have knock because you can achieve high load only by injecting more. When you inject more, phi is increasing. When phi increase, with increased phi and premix combustion, you may have a knocking kind of combustion. This is exactly the problem we are trying to address through engine design and fuel modification. Conventional fuel and design will have this inherent problem. Actually, we have been successful, I would say that to some extent. What we have observed here is instead of diesel, if I run diesel engine with gasoline in this premix mode, I am able to achieve complete load range. One of my recent graduate PhD student has done this. In fact, he received the Institute Research Award for the same concept. That is what he investigated. He has shown that his research has shown that if you run diesel engine with gasoline or petrol, right, in a premix lean combustion mode, you can completely eliminate soot and NOx. You can achieve high load also. Because gasoline is a high octane fuel, it avoids knocking.
So it will run on dual fuel mode, sir?
No, only gasoline, Only gasoline, but we have some problem at low load. What we have done is we have used ignition improver additive like EHA. Only at low load conditions you need that, because that improves combustion stability at low load, because it's a high octane fuel, right?
Right, sir.
Sir, one doubt.
Yeah.
Sir, diesel engine, basically it was a heavy weight, no sir, crankshaft, everything. If you put petrol, torque, everything, it will come less only, no sir, compared to.
No, what I'm saying when I say that I'm running in a premix mode, I'm not compromising anything on the power output. Same power output, but in a premix mode.
Okay.
Okay, so that's what one of you asked about going to high load. High load, there was some problem. We are trying to address that through changes in the engine design and changes in the fuel. An example I have just said just now is about using gasoline instead of diesel as a fuel. That is only one example. Likewise, we have investigated several other strategies in terms of design and fuel. And I can say that we are successful to some extent in achieving wider load range. Okay.
Sir, I'm sorry to ask this stupid question, but the thing is, if I'm using only gasoline at the low load condition, then it's a gasoline engine. It's not a diesel engine anymore, right, sir?
So base engine is diesel engine, right? Not a gasoline engine. I'm using gasoline and a diesel engine. I can say that.
You mean to say that
so it's a gasoline GDI?
Not GDI. It's a gasoline with a port injection. To create pre-mixing, I'm not injecting directly. I'm injecting gasoline in the port. So I can use a conventional port fuel injection system. Again, that is another advantage. You don't need a high pressure injection system.
Sir, is your research aimed to current diesel engine can be run with the?
Yeah, that is what we have proven. Current diesel engine can run with gasoline PFI system, in this combustion mode, not in conventional mode. Okay.
Got it.
Okay, next we are looking at after treatment control system. What we have discussed so far are in-cylinder control. In after treatment control, the focus is to reduce pollutant. Hello?
Sir, normally, only one question, sir. Normally in petrol engine, petrol and CNG we are using, correct, sir? In this technology, diesel, any multiple fuel can be used. Anything is there, sir, currently, from your knowledge?
So you are talking about dual fuel engine?
Exactly,
yes.
sir.
You told us, no.
Dual fuel engine, you can use any high octane fuel as a port injected fuel. Mostly gaseous fuels are used as a port injected fuel like CNG, hydrogen or biogas. They are injected in the port. But the problem with this fuel is they cannot ignite by itself. C10 number is very, very low. So you are injecting diesel directly into the engine cylinder to ignite this pre-mixed fuel air mixture. And any of the high octane fuel can be used in the dual fuel mode, because anyway you have diesel as an ignition source.
So once starting diesel, if we ignite and later on we will
No. You have to use diesel as a pilot fuel throughout the operation, because this pre-mixed gaseous air mixture cannot ignite by itself. So you have to ignite it with the direct injection of diesel.
So just to clarify, it's basically there is a difference between dual fuel and biofuel. So dual fuel means it's using both the fuels.
No. Can you say it again?
Sir, for dual fuel means both the fuels are being used simultaneously on each combustion cycle. Whereas
Yes.
biofuel is either this or that fuel can be.
Yeah, okay. That is a flexi fuel. So you can design engine in such a way that you will be able to run with a different fuel. But that fuel alone will be used at once, sole fuel.
Right. Okay.
Okay. So next we are moving to after treatment control, wherein we reduce the pollutant concentration, not in the cylinder, but rather in the engine tailpipe or exhaust pipe. So you need some additional devices to carry out this option, after treatment control option. So you have to use an after treatment device fixed in the engine tailpipe, and that device will reduce the pollutant level before the gas is discharged into atmosphere. This is what is after treatment option. So there are two broader classification of this after treatment method. One is thermal route, or in the thermal route we use something called a thermal reactor. The second option is catalytic route. In the catalytic route, we use catalytic converter, meaning we use some type of catalyst. You know what a catalyst will do? It won't participate in the reaction, rather it will speed up. It will speed up the reaction. Okay, that is what is a catalytic action. So you have two broader route. One is thermal route, wherein we rely on temperature to reduce the pollutant level in the exhaust tailpipe. This is applicable only for SI engine, and this is applicable for controlling only HC and CO. You cannot control NO using thermal reactors. Second option, catalytic converter option, can be used both for SI engine and CI engine. Okay, and this can be used for controlling NOx, particulate. Okay, this can be used for controlling HC, CO, everything. All the four primary pollutant in both the engine, SI and CI engine, can be controlled through the catalytic route. So this is one of the most effective route, and this option is not generally used now. Okay, it has been taken over by the catalytic converter. But just to understand the principle, I have listed out here. Now let us quickly look at what this thermal reactor is, which is applicable for spark ignited engine. So what they will do in a thermal reactor based control, they will completely insulate the exhaust manifold, including right from the exhaust port. Everything will be insulated to avoid heat loss, because this method rely on the available temperature in the exhaust gas. You know, exhaust gas temperature, already we have discussed the condition. Only in SI engine you have a high exhaust gas temperature, right from 300 to 1000. CI engine you have a very low exhaust temperature, 100 to 500. That's why we cannot use this thermal reactor option for CI engine. That is ruled out because gas temperature is less. SI engine you have a high gas temperature. We want to utilize this high gas temperature to oxidize HC and CO. That is what I am talking here in terms of thermal reactor. But the problem is, although exhaust gas temperature is high, due to heat loss, the temperature will come down. For that, what is done in a thermal reactor is they will insulate the system, entire exhaust line, okay, to avoid heat loss. They will also increase residence time by increasing the volume, available volume in the tailpipe. They will enlarge the volume, as you could see here, and this enlargement in the volume is going to increase the residence time. Residence time is the time at which the gas stays in the tailpipe, right? If you have a simple flow area, the gas will flow quickly. The flow velocity is a function of area, flow area, right? You know that. So we are increasing the area here intentionally so as to increase the residence time. So two things we are doing here to rely on exhaust gas temperature to oxidize SC and CO. One, insulation, the complete exhaust line. Second one, increase the volume and thereby increase the residence time so that the gas stays in the exhaust line for longer time. Because of that, the SC and CO will be oxidized. SC will be oxidized to H2O and CO to CO will be oxidized to CO2. We have already discussed the oxidation temperature. If you relook at here, temperature you need is around 600 degree and above for Sc oxidation. Temperature you need is around 700 and above for CO oxidation. We are trying to create that ambience here in the thermal reactor. Thereby, we are trying to control Sc and CO. This is not effective because exhaust gas temperature varies based on the engine operating temperature. Sometimes it is very low. For example, at the time of just starting the engine or low load condition, the gas temperature is considerably less. So you cannot effectively reduce Sc and CO in the tailpipe because of this reason. Is it fine if I take a few more minutes? It's already time up. Hello?
Yes, sir. Please continue, sir.
Okay. So I was
no issue, sir. Please continue.
Okay, fine. So the second option, which is the most effective option, is catalytic converter, which is applicable for both SI and CI engine. For SI engine, there is only one device that effectively control all the three primary pollutant, NO, SC, and CO. The device that we need is a three-way catalytic converter. A three-way catalytic converter can simultaneously reduce NO, SC, and CO to a very high proportion. Generally, we use the term conversion efficiency. Conversion efficiency is about how much of these pollutants are reduced. Conversion efficiency for three-way catalytic converter is generally about 90%. So more than 90% of these pollutants are reduced in the tailpipe if you have this device installed in your tailpipe. So that's why I would say that in SI engine, the pollutant control is straightforward compared to CI engine. It's less complex here because we have one device that can effectively control all the three primary pollutants to a level of above 90%. Now let us quickly look at the principle involved. So this is a schematic of a three-way catalytic converter. It's like a small metallic can. This is installed in the tail. This is tailpipe. So you have this. You would have seen this in passenger cars, right? Most of you would have noticed this. You have a metallic can here, enlarged area, metallic can. Inside the metallic can, if you look at, you have something called a honeycomb structure. Okay, this is called a wash coat. This wash coat is made up of ceramic material. Okay. Aluminum oxide is generally used as a material to construct this, okay, because it doesn't melt, okay, it can withstand higher temperature, okay. So you have an alumina wash coat that provides a surface for dispersing catalyst. So you have a honeycomb structure. This structure is called honeycomb. You have a large surface area with a given volume. That's why it's a porous structure, it will have a large surface area with a given volume. Why we need a large surface area here?
Residence time increase.
Residence will be enhanced if you have a large surface area. That is the reason. So you have a metallic and you have two beds here. This is a reduction bed wherein all the reduction reactions will happen. For nitric oxide, you have to reduce. Okay, so this reduction bed basically convert NO to N2. NO is reduced to N2. The second one is called oxidation bed. So in the oxidation bed, what we do is Hc will be converted to H2O, CO2. It's an oxidation reaction. CO will be converted to CO2. It's again, so in the oxidation bed, what is happening? Oxidation reactions are happening. In the reduction bed, reduction reactions are happening. NO is converted to N2. How do we do that? NO will react with so these reactions are called reduction reactions. This is what is happening in the reduction bed. Okay, and these reactions happen in presence of reducing gases. So what you need to have is reducing gases. Reducing gases are products of rich mixture combustion. Reducing gases example is CO, H2, any hydrocarbon. Okay, these are products of rich mixture combustion. For oxidation, what you need is oxidizing gases. Example O2 or any radical, any oxidizing radical like OH. We have seen OH is a oxidizing radical or O radical. These radicals are available at a larger extent inside the cylinder during combustion, core combustion, because you need high temperature. In the exhaust line, it's very difficult to get the radicals because generally you have stable species in the exhaust. For example, you need to have oxygen. So you have a conflicting requirement here to control HCCO, NO simultaneously. For controlling NO, what you need is reducing gases, which are products of rich mixture combustion. To control HC and CO, what you need is oxidizing gases, which are products of lean combustion. So you have a conflicting requirement here in terms of rich. You need both rich mixture products as well as lean mixture product. This is one of the reasons why we run SI engine close to stoichiometry. What we want to ensure to have a high three-way catalytic converter, we want to ensure that we have sufficient reducing gases in the engine exhaust. We also have sufficient oxidizing gases in the engine exhaust. If you deviate from stoichiometry or slightly rich, you will have a problem of having this oxidizing and reducing gases both. This is also one of the important reasons, apart from flame stability. This is also one of the reasons why we have a narrow V equal to 1 operating regime for spark ignited engine, unlike compression ignited engine. Okay, so we have two beds here. One is a reducing bed, second one is oxidizing bed. And what we will have in this bed, finely dispersed catalyst. Reducing catalyst is rhodium. We have different catalysts here, metallic catalyst. Rhodium is a catalyst used for reduction reactions. For oxidizing reaction, the catalyst required is platinum and palladium. The ratio is around 2. Platinum is effective in controlling HC and palladium is effective in controlling CO. That's why we have both platinum and palladium in the ratio of 2 that is finely dispersed here in this wash code. So on this catalyst size will be typically 20 nanometer size. So you have finely dispersed catalyst in this wash code. Okay, the wash code is covered with a metallic can. You have high surface activity happening here. How the reaction will happen is when the exhaust flow through this, there will be absorption of gases over the wash code where you have finely dispersed catalyst. In presence of catalyst, these reactions are happening, reduction reaction here. And if it reaches oxidation bed, oxidation reactions are happening. There you have these catalysts finely dispersed over the wash code. In presence of catalyst, in presence of these oxidizing gases, HC and CO will get oxidized to H2O and CO2. Now here in the reduction bed, in presence of these catalysts, in presence of these reducing gases, example I have given is CO and H2. In presence of these gases, whatever NO present in the engine exhaust is converted to N2. So what will come out is H2O, CO2 and N2. Okay, so you are converting or reducing all the primary pollutant and letting out only H2O, CO2 and N2. I already said that the conversion efficiency is more than 90%. Okay, so this is what we are doing here with this three-way catalytic converter, and there is something called the light off temperature. There is a minimum temperature at which most of the catalysts, almost more than half of the catalysts will be active. That light off temperature is around 250 degrees Celsius. So only thing you need to ensure is you have at least this minimum 250 degrees Celsius so that the catalyst is more active. Catalytic activity is also dependent on the temperature level in the exhaust line. But generally in SI engine, you will have this 250 degrees Celsius available, so you don't have any problem. That's why this system is a successful system in spark ignited engine that can effectively control all the three pollutants. Clear? Is it clear?
Yes, sir. Yes, sir.
Yes, sir.
Okay. So we have seen only one device for spark ignited engine, but the problem with CA engine is you need different devices as indicated here. To control SC and CO, what you need for a diesel engine is a DOC. DOC is diesel oxidation catalyst. Okay, diesel oxidation catalyst is used to oxidize SC and CO in the engine exhaust to H2O and CO2. The construction of DOC is similar to what we are seeing here for the three-way catalytic converter in this oxidation bed. So what you need here in the DOC is not the reduction bed, only oxidation bed. So the construction is exactly similar, but there are some small differences I will highlight. So you need this DOC, which will look like exactly same as oxidation bed present in a three-way catalytic converter. You have a wash port, you have finely dispersed catalyst, exhaust gas is allowed. You know that in a diesel engine already you have high levels of oxygen. So in presence of oxygen, SC and CO will be oxidized to H2O and CO2. This is what is happening in a DOC. But before that, I have a question to you. Why we have arranged the reduction bed before the oxidation bed in this converter? What will happen if you do it other way?
Sir, like if you do a opposite way, then what I mean to say is, again it will get oxidized, reduced. Like what I mean to say is, we have SC and CO. If we oxidize it to CO2 and H2O, and again we are sending to reduction bed, it will again get what I mean to say is like converted to CO. Possibility is there.
Okay. The major problem is what you need for reducing reduction reaction is rich products. Okay. When you keep oxidation bed ahead of the reduction bed, you're going to convert all these rich products in the exhaust line. This is going to be oxidized. So you will run short of this rich products of combustion when you arrange the oxidation bed ahead of the reduction bed. For example, look at the reaction here. NO is converted to N2 in presence of H2. H2 is available only with rich products of combustion. Similarly, NO is converted to N2 in presence of CO. If you arrange an oxidation bed ahead of the reduction bed, you will run out of CO because CO will be oxidized to CO2. Did you get what I am saying?
Yes, sir. Yes, sir.
Okay, so we have this diesel oxidation catalyst. So what is being done here is same oxidation reaction, SC and CO coming out of the engine tailpipe will be oxidized to H2O and CO2. So it's basically an oxidation reaction happening in the DOC in presence of catalyst. Catalyst used is platinum in this device. The only difference is the wash coat material cannot be alumina. Instead, you have to use either zirconium oxide or silicon dioxide. The problem with alumina that we have discussed for three-way catalytic converter is this alumina will react with SO2 or SO3 and form aluminum sulfate. Right? Because in diesel, compared to gasoline, you have a high sulfur level. So you have these oxides available in the engine exhaust. So you are not supposed to use this material for wash coat. Rather, you have to use a different material, silicon dioxide or zirconium oxide. Conversion efficiency is generally low. The problem is you need high temperature as indicated here. Why I say high temperature? Because you see this is effective only at temperatures up to 350 degrees Celsius. Sometimes in diesel engine, you have a very low exhaust gas temperature because you use XSR. So because of that, the conversion efficiency of CO is around 40 to 90. 90 if the temperature is high. When the temperature is lower, you will have a very low conversion efficiency. Similarly, SC 30 to 80. Okay, so the conversion efficiency will be less when the temperature drops considerably. Okay, so it will be either high or low based on the temperature level. Basically, so did you get what I am saying? Based on the operating temperature in the engine exhaust, right? It can be lower or higher. If the operating temperature is high, exhaust temperature will also be high. So you will have a high conversion efficiency. If the temperature in the exhaust line is lower, then the oxidation rate will come down in the DOC. So you'll have a lower value of conversion efficiency. Is it clear?
Yes, sir.
Next, we have this LNT. So to control NOx from NOx is oxides of nitrogen, control NOx from CA engine, either you can go for lean NOx drop or you can go for selective catalytic reduction. You can use this device or lean NOx trap or selective catalytic reduction device to control NOx from compression ignition engine. This lean NOx trap is generally used for light duty vehicles, small vehicles, diesel vehicle, and selective catalytic reduction is generally used for heavy duty vehicles. This lean NOx trap system is compact system, but conversion efficiency is poor. That's why it is preferred for light duty applications since you have a space constraint. Heavy duty engine, you have more space, so you can go with selective catalytic reduction because it has a high conversion efficiency. So this is being used for heavy duty application. This is being used for light duty application. Now let us quickly look at how this lean NOx trap works. The construction is similar to what we have seen for three-way catalytic converter, but what we do here is in a lean NOx trap, to reduce NO, you need reducing gases. That is what we have discussed just now. Reducing gases are products of rich mixture combustion. In a diesel engine, we never run with rich mixture, right? We always go with lean combustion. 30 to 50% XSR is used. We have already discussed about this. So it's very difficult to have this products of rich mixture combustion in the diesel exhaust as such. In a normal operation of a diesel engine, you won't get these products of rich mixture combustion because you always run under lean condition. Overall global equivalence ratio, 0.4 to 0.8 at the most. Okay, so it's well below 1. So you always have XSR in a diesel engine. You don't get this rich mixture combustion. Without this reducing gases, you cannot reduce NO and NO2 to nitrogen. Basically, we want to convert NO to N2. This is what is a reduction reaction. We also want to convert NO2 to nitrogen before the gas is discharged into atmosphere. By using this LNT device in the tailpipe, we want to convert NO and NO2 to nitrogen. And we want to discharge only nitrogen in the ambience. But what we need is reducing gases. This is not available in a normal diesel engine combustion because we go with lean combustion. So what we do in a LNT system, we create this reducing gases, which are products of rich mixture combustion, by having a very late fuel injection during the expansion stroke. So during expansion stroke, you just spray the fuel for few seconds. Okay, few seconds, you just introduce a fuel spray during expansion stroke. Okay, not the compression stroke. So during expansion stroke, if you inject this fuel, what will happen? This fuel will partially oxidize. It will create CO, SC, H2. All the rich products of combustion will be created in the engine cylinder, and that will come out in the exhaust. We are going to utilize this reducing gases to reduce NO and NO2 to nitrogen. So this is what we are doing in a lean NOx trap. What is done is you have to first convert all the NO to NO2 in presence of a platinum catalyst. So there is an oxidation reaction happening. The construction is similar to what we have discussed for three-way catalytic converter. That is a wash coat. In that wash coat, you have a catalyst. The catalyst used here is different. Okay, so the catalyst used here is platinum alone, and this platinum is going to convert NO to NO2 through oxidation reaction. All the NOx is now present in terms of NO2. What we do with this NO2 will go and get trapped in the system, LNT system. That's why it is called lean NOx trap. How it is trapped, this NO2 will react with something called BaO. BaO is barium oxide. It's called an alkaline earth metal. So what we have in the same wash coat, you have platinum, you also have this barium oxide. So once you convert all the NO to NO2, this NO2 will react with this barium oxide in presence of oxygen and form barium nitrate. So you are basically converting all the NOx to barium nitrate in this LNT device. So you are trapping NOx in terms of barium nitrate and storing it in the device. That's why this device is called lean NOx trap. Convert all NO to NO2, NO2 react with BaO and form barium nitrate. Once the system gets saturated with barium nitrate, you spray fuel during later part of expansion stroke, create rich products of combustion. Now in presence of this rich products of combustion, this barium nitrate will be converted to nitrogen. So the reaction that will happen is this barium nitrate will be converted to, in presence of SC, rich products of combustion. This will be converted back to BaO. Okay, and then what you will have is N2, H2O, and CO2. Okay, so basically you are converting barium nitrate to nitrogen in presence of rich products of combustion. One representative hydrocarbon I have indicated here. So it can be CO, it can be H2, or it can be any hydrocarbon. This you are creating by spraying fuel during later part of expansion stroke. So this rich products of combustion are available. This barium nitrate get converted to BaO along with nitrogen. So you are trapping NOx in terms of barium nitrate and converting that NOx to nitrogen before the gas is released into surrounding ambience. This is what we are doing. Typical molar ratio that you need to note down here is 2 to 5. 2 to 5 is the quantity of fuel that you need to inject based on the NOx level. You need to sense the NOx level in the exhaust line. Accordingly, you need to fix the injected fuel quantity. So molar ratio is 2 to 5 of SC per mole of NOx. Okay, this is a typical split calculation that you need to do to fix the quantity of fuel you are injecting during the expansion stroke. So you create artificially rich products of combustion, right? And this rich products of combustion react with barium nitrate, which is already there in the LNT system. And using this rich products, you are reducing the trapped nitric oxide into nitrogen. So this is a typical selective catalytic reduction system, SCR system, which we have to control NOx in heavy duty engine. So in a selective catalytic reduction system, what you have is a DEF. So this DEF is diesel exhaust fluid. Diesel exhaust fluid consists of 30 to 40% urea plus 70 to 60% water. This is what is DEF, diesel exhaust fluid. Okay, so you store it here. Basically, in this system, ammonia is used as a reducing agent. Instead of rich products of combustion, ammonia is also an effective reducing gas. So what this gas will do is it will convert NO or NO2. It will convert it to nitrogen. So basically it is doing a reduction reaction. Ammonia is an effective reducing agent. We use the word reducing agent. Ammonia is an effective reducing agent that can reduce NO or NO2 to nitrogen. Okay, so ammonia, it's a pollutant. That's why we don't carry ammonia directly in the vehicle. Rather, we carry it in the form of DEF, diesel exhaust fluid, okay, which is 30 to 40% urea with water. So once you store it, you are going to spray that urea in the exhaust line. That's what we are doing here. This is a SCR, selective catalytic reduction unit in the tailpipe. Once you spray this urea will release ammonia. Urea will be converted to ammonia. This process is called hydrolysis process. So you are storing diesel exhaust fluid and spraying it using an injector in the exhaust line. In presence of exhaust gas temperature, this urea will get converted to ammonia. Okay, this ammonia will go to this SCR bed. In the SCR bed, construction is again same as what we have discussed earlier, but the catalytic material is different here. Vanadium and titanium oxide mixture will be used as a catalyst. In presence of that catalyst, ammonia will convert NO or NO2 to nitrogen. Okay, so and then the clean gas will be let out into atmosphere. You have to carefully fix the injected quantity of DEF, otherwise you will have excess ammonia, that is called ammonia slip. This is the only complexity with the system. You need to carefully monitor and inject the DEF quantity so that you don't have any excess ammonia going through the exhaust line, because ammonia is a pollutant. So we should avoid this. Okay, ammonia slip should be avoided. How it can be avoided? You have to carefully monitor the NO level, NOx level in the exhaust line. Accordingly, you have to fix the injected DEF quantity. So I will just show the typical reactions, chemical reactions. So you have the first step is hydrolysis. This is urea. So you have a DEF, diesel exhaust fluid, which is a mixture of urea and water. As I said, urea and water, when you spray in the exhaust line, the exhaust temperature is enough to cause this reaction, hydrolysis reaction, wherein you could see that ammonia is generated along with CO2. Okay, this ammonia is now undergoing reduction reaction in the catalytic bed. The catalyst is a mixture of vanadium and titanium oxide. So you have a construction similar to three-way catalytic converter I have shown earlier. The catalyst material is different. You have a wash coat. In the wash coat, you have this finely dispersed catalyst. In presence of this catalyst, ammonia is converting NO and NO2 to nitrogen. So there is a reduction reaction happening in the SCR bed. Through the reduction reaction, you are converting both NO and NO2 to nitrogen, and the clean gas is let out into atmosphere. The typical molar ratio is around 0.9. This is a typical molar ratio of ammonia to NOx, okay, which you have to carefully fix, otherwise you will have a ammonia slip. If you inject excess of DEF in the exhaust line, you will have excess ammonia that leaves the engine tailpipe. Ammonia, you know, it's a pollutant, so ammonia slip should be avoided. Because of, to avoid ammonia slip, you have to carefully fix this molar ratio. The injected quantity of DEF has to be according to this ratio. Ammonia to NOx is 0.9. Okay, the last one after treatment device that you need for diesel engine is particulate filter, DPF, diesel particulate filter. Okay, this is so in the PM particulate matter, already we discussed the composition. The primary component in the particulate matter is soot, solid carbon particle. So to remove the solid particles in the exhaust line, what you need is a filter. So that filter is referred to as either diesel particulate filter or simply particulate filter, which is what is going to filter out the exhaust gas from particles, and clean exhaust gas will be let out into atmosphere. So this filter will be installed in the exhaust line. I have shown the typical location here. You could see. There is a reason behind locating diesel particulate filter before SCR, selective catalytic system. I'll talk about that. So you have this filter, DPF, diesel particulate filter installed here. This is going to filter out the exhaust gas, remove the particles. Clean exhaust gas will be let out through the line, exhaust line. So there are different types of filters that can be used. One of the most widely used particulate filter is shown here. It's called ceramic wall flow filter. So the ceramic wall flow filter has a circular cross section. It's having a honeycomb structure, as you could see here. This is done to increase the surface area. So when you look at more closely a sectional view, you could see that there are open end. You have cells, n number of cells, which is open at one end, closed at the opposite end. And alternate cells are open at one end and closed at other end. So here on the upstream side, the gas will enter through the open end. It cannot leave through this end. Rather, it has to leave across this wall. This wall is a porous wall, the porous wall. So in the process, what will happen is when the gas tries to leave through the porous wall, all the particles loaded in the gas will be removed or filtered. So this act as a filter, remove the particles here. Clean gas only can leave. Since this end is plugged, only the other end is open. So at the downstream end, through the open end, the gas will leave, clean gas will leave. So it has to pass through the open end in the upstream side, right? It cannot leave through the other end in the same cell. Rather, it has to cross flow through the adjacent porous wall. So during this process, the particles are being removed here. Clean gas will be let out through the open end in the downstream side. So all the particles will get collected here, and it's a ceramic material which is having very high melting point. It won't melt because you deal with, I will talk about regeneration. So you are dealing with that. So the temperature reach will be high. So it should not melt or expand under those conditions. That's why we use a ceramic material here. Also, to increase surface activity, you have a high surface area here. So the particles will get collected. The problem is once the particles are collected, you will have a pressure drop in the exhaust line. You will have a very high back pressure in the exhaust line, and that will reflect in very high fuel consumption in the engine. So what you have to do is you have to periodically clean the particles collected here. This process is called regeneration process. So there are two types of regeneration. There are two types of regeneration as indicated here. One is active regeneration and other one is passive regeneration. And once a particle reaches this threshold limit, you could see a threshold limit, 10 gram per liter. Liter is the capacity of the DPF. Once a particle reaches this threshold limit of 10 gram per liter, you have to start this regeneration process. So you need to carefully monitor the pressure drop in the exhaust line using a sensor, and then start this regeneration process, which will continue for 8 to 10 minutes, and the filter will be cleaned. So to clean the filter, you have either an active option or passive option. In active option, what you do is you are going to burn the collected soot by increasing the temperature. Okay, the temperature you need to, soot is solid carbon. The temperature you need to oxidize it is around 500 to 600 degrees Celsius if you don't use a catalyst. So in active option, you are using without catalyst. You are burning the soot without catalyst. That is what's the active regeneration option. In a passive regeneration option, you are going to use catalyst. The advantage in using catalyst is you could see that there is a significant drop in the temperature required to oxidize soot in presence of catalyst. So in presence of catalyst, you can oxidize soot at a temperature as low as 200 degrees Celsius. So that's why passive is generally preferred option for regeneration rather than active, because you need a high temperature here. So you have to use either electric heater or an external heating source to raise the temperature of the exhaust gas to oxidize soot. Otherwise, the regeneration won't happen. So generally, we prefer to go with passive option because the temperature required for oxidation is less, around 200 degrees Celsius. You need a catalyst. The catalyst, surprisingly, the catalyst, one of the most effective catalyst is NO2. NO2, nitrogen dioxide, is one of the most effective catalysts that can help in oxidizing soot at a lower temperature. This is exactly the reason why we located, here you could see that the DPF is located before SCR, because we want NO2 as a catalyst in the DPF. NO2 is required as a catalyst for the DPF. That's why we locate DPF before SCR. Otherwise, in SCR, you are reducing NO2 to nitrogen, right? If you reduce it, you don't have a catalyst for the system. That's why you have to carefully arrange the after treatment device. You need more than one device for diesel engine after treatment control. So you have to arranging this devices properly is also an important task that you need to look at. Okay. Like I have said, you have to have a reduction bed followed by oxidation bed in a three-way catalytic converter. Similarly, here in a diesel engine after treatment system, you need to have a DPF located before SCR. So these are important points to be noted from a practical implementation perspective. It's already time up, excessive time. I'm sorry for taking another half an hour. I close here. I will complete the chapter, remaining 2 short chapters by tomorrow. So tomorrow, I think I should be able to complete this course. If you have any questions, I can take your questions.
Yes, sir. So tomorrow 5 o'clock, no, sir. Same time.
Yes, tomorrow we will have class at 5 o'clock.
Sure, sir. Okay, sir.
Any doubts?
Sir, just on the exam point of view,
Okay.
more weightage will be on the second half of the semester, right?
The contents discussed after quiz 2.
Quiz 2, right?
Yes.
Till the end of what you're teaching till tomorrow.
The entire syllabus is what you have to go through. Entire syllabus you have to go through for the end exam. Okay. There will be questions asked from quiz 1, quiz 2 syllabus also. But what I'm saying is in terms of mark split, the weightage will be given less for those. The weightage will be given in the sense that more marks will be given for the contents discussed after quiz 2.
Okay, sir. Thank you.
Okay.
Sir, the in some mark, how much is it? Like midsum is 30 mark, like that.
End sum is for 100 marks, 3 hours.
Okay, sir.
Okay, so I'll stop here. I'll meet tomorrow at 5 o'clock. Thank you.
Thank you so much, sir.
Yeah.
Thank you, sir.
Thank you.
Thank you. Bye.
Thank you, sir.